Hello and welcome back to my channel. Today we're going to be talking about what to do if integration by parts or partial fraction decomposition doesn't make sense to do. So if we look at this problem here, we have the integral of x cubed minus 1 over x minus 2. This doesn't have a denominator that needs to be split up, so we can't really do partial fraction decomposition. The other thing is the numerator is bigger than the denominator's degree, so either way we'd have to do polynomial division to begin with. If we tried to do u substitution, we would normally make the denominator equal u, but it's not really helpful here either. So knowing that we're going to have to do knowing we're going to have to do polynomial division of some sort, that's kind of where we're going to start here. We're going to start by doing any sort of polynomial division, the fastest being long division. So if we do polynomial long division, we have our half box here. Inside the half box is going to be what makes the denominator equal to 0. X minus 2 will equal 0 when x is 2. And then we are going to do the coefficients starting at the largest degree and working our way down to the ones place. So our biggest exponent is x cubed. We have one of those. X squareds, we have 0. X to the first, we have 0. And then in our ones category, things without x's, we have negative 1. We're going to bring our first term down. We have 1 below the line, so we're going to multiply it by the thing in our half box. So 1 times 2 is 2. And then we add 0 plus 2 is 2. And then I repeat, 2 times 2 is 4, 0 plus 4 is 4, 4 times 2 is 8, negative 1 plus 8 is 7. This time, we don't really care if we get a remainder or not, so it doesn't necessarily have to divide it equally. And then when I rewrite my problem, the first term here is going to go with the second largest, and it goes down the line from there, going all the way down to our remainder. So that tells me I have 1x squared plus 2x to the first plus 4 plus a remainder of 7, which means we have 7 divided by what we divided by originally, x plus 2. So what this tells me is that this integral is the same thing as x squared plus 2x plus 4 plus 7 over x minus 2 dx. I can take the derivative of each of these things individually. It's the derivative of x squared, x cubed over 3, plus the derivative of 2x, 2x squared over 2, and the 2's cancel out, plus the derivative of 4, and then the derivative of 7 over x minus 2. Because we have an x minus 2 in the denominator, I know that's going to be a natural log. So we have 7 times the natural log of the absolute value of x minus 2. And then because we took an integral and it's an indefinite integral, I add my constant plus c. So when I do something, if I ever have the numerator's degree is bigger than the denominator's degree, I always need to do polynomial division to kind of help me out. Now, in this case here, we have the numerator has nothing in it, which means 1. If we look at what we have, I can't really make the denominator equal u because I need a 2x plus 10 in there somewhere to kind of offset everything else. Things that multiply to 26 and add to 10, I don't think we have any solid numbers that are going to work for us on that. The closest we can get is 2 and 13, but that doesn't add to 10, so it's non-factorable for us. So we need to try something else. And that something else is this method called completing the square. Now what completing the square does is it takes something in that standard form and turns it into our transformation form, our vertex form. Okay, so we're going to focus on just the denominator for a little bit, and then we are going to go back to our problem. So our denominator is this x squared plus 10x plus 26. A lot of times when we're doing completing the square, we end up setting this equal to 0. And it's going to just be like a placeholder for us for a little bit. We could say y instead. We just want something there so that way we can move some stuff around as we need. When we complete the square, what we want is we want to remove the ones just to make this process a little bit easier. So the first thing that we're going to do is take away 26 from both sides to give us x squared plus 10x. That negative 26 isn't going to stay there forever. It is going to move back over eventually, but for right now we need it a little bit away. So what we need to do is we need to figure out what we need to add to both sides to make this a perfect square. And our perfect squares need to look like x plus or minus h squared. So what we mean by this is that I can think about this in algebra tiles. So this right here is x squared. In order to get x squared, I need an x times an x. I only have one x squared, so this kind of takes care of that x squared piece. I have 10x to the first. Well, this side right here is a length of x. This one right here. And this side is a length of x, which is how this became x squared. So I'm going to use that. And we are going to also add in a smaller little chunk here. This is going to be a 1 by x. So this is a 1x. We have 10 x's in this, and we need this split in half. Like, we need this to be the same on both sides. So I'm going to put 5x to the first on this side. Four, 5. Well, that was all sorts of bad. So this right here is 5x. And we have it on this side too. It's not my best squares, but you know, it gets the job done. Okay, each of these sides right here is 1, so we have a plus 5 on both of these. So if this is what I want, then I want this to be x plus 5 times x plus 5. We have the x squared and the 5, or the 10 total x to the first powers to kind of help us out here, but what we want is we also want these 1's values. So each of these sides is 1, and then each of these sides is worth 1. So if we kind of put all of this together, then I need 25 1's in this space right here, which we don't currently have. So what we're going to add to both sides is 25 in order to account for those 25 1's that we need in our problem. So I have x squared plus 10x plus 25 is equal to negative 1. So one of the things that you can also use instead is, if we don't like having to do this every time, we can also use the formula that they have for us. Our formula that we can always do for the thing that we're adding is negative b over 2a squared. So we take that second value, our b value, negative b over 2a squared, that comes from the quadratic formula. But negative b over 2a, if I look at it in our problem, this is our b, so negative 10 divided by 2 times 1, so divided by 2, which gives us 5, and then we square it as 25. So we get the same thing no matter what. Okay, so now if I look at this, we have x squared plus 10x plus 25. If I were to factor that out, I'm going to get an x plus 5 and an x plus 5. That's why we chose the 25. So I have x plus 5 squared. And then we're going to move that negative 1 over. So we get x plus 5 squared plus 1. Okay, so now what we're going to do is we're going to put it back into our problem. So our original problem was the integral of 1 over x squared plus 10x plus 26 dx. And now we know that equals the integral of 1 over x plus 5 squared plus 1 dx. So one thing that we have to know is that this is a very specific integral, and this integral happens to look like an inverse trig function. Specifically, it's going to remind us of tangent, and the way I can tell is that we have a squared here, and 1 squared is still 1. So when I'm looking at the formula for inverse trig, it a lot of times has u and a. So we're going to make u equal to x plus 5, and we are going to make a equal to 1. Our rule for inverse tangent, or arctangent, is if we have the integral of 1 over a squared plus u squared, u being our thing with x's, du, and that's how I know it's the one with x's. This is going to give us 1 over a tangent inverse of u over a plus c. So if we kind of follow that same thing, 1 over a is 1 over 1, but 1 over 1 is 1, so we don't actually need it. So we have tangent inverse of u over a, so we have an x plus 5 divided by 1, which is just x plus 5 plus c. A lot of the times, if you have to do completing the square, it generally is going to mean that we need to do some sort of trig inverse, most likely. So that's just one to keep an eye out for.